Hello friends, welcome to CSL. So today we are going to continue with the PWD AE 3F question paper, and we are on the third video of the structural engineering. Okay, so today we are going to start with the design questions, okay, of structure, design of structure. So 10 question came, okay, 10 question came only, and mostly these are from RCC, okay, and 2 I think it's from steel. Okay, so this is a very important topic for any type of competitive exam, so don't miss this. Okay, so let's start with the design part. Okay, so the first question came is that a simply supported beam 250 mm wide and 450 mm deep to the center of tensile reinforcement. Okay, so you should have the basic knowledge of this. The center of tensile reinforcement, this is the cross section of the beam. Okay, this is given as 250 mm, and tensile reinforcement, this is the tensile reinforcement because this is the cover, we have to give the cover, and this is the effective depth which is given as 450. Okay, so the limiting moment of resistance of the beam section for M25 grade of concrete and Fe 415 grade of steel. So we have to find the limiting moment of resistance, means MU limit. So for MU limit means it's the maximum moment, okay, that the beam can carry. Okay, so the formula for MU limit, it's given as, either you can use two formula, either you can use this one FCK B XU D minus 0.42 XU. Okay, this is a very important formula, you have to memorize it. Okay, or 0.F1 AST D minus 0.42 XU. So basically means from the compression side and from the tension side. So if this is the beam, okay, this is the tensile reinforcement. So the stress diagram, something is given like this. Okay, so this is the lever arm. Okay, so I will not go in detail. Okay, you should know all this. This is the basic. So these two formula you can use either of them, but in the question nothing is mentioned about the area of steel. Okay, AST is not mentioned, so if it is not mentioned we cannot use this formula, we have to go by this one. Okay, so MU limit, the formula should be this one, limit. Okay, so this is XU limit. So from this, in the question FCK is given, it's given M25, so FCK it's given as 25 Newton per mm square. Okay, B it's given as 250 mm. XU limit I don't know. D is the effective depth, is given as 450 mm. Now what is the XU? XU is the, if you know, it is the depth of neutral axis. Okay, depth of neutral axis. So and XU limit is the maximum depth. Okay, so in the limit state of design, okay, see we have two, one is working and one is limit. Okay, so whenever you have to design a beam, always go for limit state. If it is not mentioned in the question, if it is mentioned, then go for working state, otherwise go for the limit state of design. Okay, don't go for working stress. So in the limit state of design, for XU by limit by D, it's given for the for grade of steel. Okay, so if it is 250, it is given as 0.53. If it is 415, okay, 0.48. If it is 500, I think it's given as 0.46. Okay, so these values you should remember, it's given in the IS code, you have to memorize this. So XU limit by D, it's given as 0.48 for 415. So XU limit by D is given as 0.48. D we know it's given as 450. Okay, it's given as 450. So XU limit will be 0.48 into 450. It's given as around 216 mm. Okay, so just put all the values in the formula. You will get 0.36, FCK is 25, B is 250, XU limit is 216, D is 450 minus 0.42 into 216. If you will get around 17461,000, something closer to this Newton. So Newton mm. Okay, so 174.61 kilonewton meter. It's not 000, there are some values are there. Okay, you can find out, and finally you will get 174.61 or 66 kilonewton meter, but in the question it's given as 174.66. okay, so we have got 174.61. so since this is the nearest value, you may not get the exact value, but if you get the nearest value, go for it. Okay, so this is your answer, 174.61. just put the value, you'll get the answer. Okay, so let me go to the next one. Okay, so the next question is given as per IS 456/2000, the horizontal distance between parallel main reinforcement bars of slab. Okay, so if this is the cross section of the beam, okay, and these are the main reinforcement. Okay, so this spacing, okay, what is the maximum spacing that can be we obtain while designing this spacing? Okay, so spacing are two types. One is the horizontal distance from the main reinforcement, and another is if we see from the side one. Okay, we'll get the, if this is the main bar, we'll get these stirrups. Okay, so this also given in the IS code, so don't confuse, it's given as main reinforcement bar, so this spacing we need to know. Okay, so maximum spacing for horizontal bar, okay, for main reinforcement, it's given as either it's 3D or 300 mm or 5D or 500 mm. if this is only if it is temperature and shrinkage effects. Okay, temperature and shrinkage effects are mentioned, then go for 5D or 500 mm. So nothing is mentioned in the question about temperature, so our answer is 3D or 300 mm. Okay, so if don't confuse with this shear one. Okay, this shear reinforcement, this as the maximum is again given as 0.75D or 300. this is for only shear. Okay, shear, so it's not given in the question, so don't confuse. Okay, 0.75D or 300 mm. so if shear is asked, so go for this one for the maximum. It's minimum of these two, so minimum of these two is the maximum spacing. Okay, that's only for shear, but since we are given the main reinforcement, so our answer will be 3D or 300 mm. Okay, now next let us move on to the next one. It's given as per IS 456, the minimum steel reinforcement in either direction in slabs for mild strain reinforcement and high strain deformed bars shall not be less than. Okay, so first of all you should know the percentage of steel. Okay, this table, percentage of steel, this table you should know. First one for beam. Okay, minimum it's given as 85/FY%. Okay, so these are all very important. Okay, anyone this question will, one of the question will come in the examination. Okay, so the minimum of percentage of steel for beam is 85 by Fy, and maximum it's 4%. Okay, for slab minimum it's given as 0.15% if mild steel is used, that means Fe 250, or 0.12% if HYSD, high yield strain deformed bars, or Fe 415 is used. Okay, and maximum again it's same as the beam, it's 4%. Okay, and 3 for column minimum it's 0.8%, maximum it's 4% if lap reinforcement is provided. Okay, and 6% if lap not provided. Okay, so these values are very important because one of the specification may ask in the examination, so please please memorize it. Okay, so in our question it's given for the slab. Okay, and we know for 0.15% for Fe250 and 0.125 for HYSD, so our answer will be D. Okay, and obviously this percentage of the cross section area, okay, means 4% of the cross section area means BD. Okay, so let's go to the next one. So it's a question from footing. Okay, so it's given as the square column 500 mm carries an axial load of 1500 kilonewton. The maximum factored bending moment for the square footing of size 2.75. Okay, so a footing is there. Okay, the size is 2.75. Okay, and the center there is a column of size 500. Okay, so a axial load is also there. So okay, so let's ignore the drawing. Okay, so it's given here, P is given, this is the column. Okay, so we have to find the factored bending moment. Okay, so the factored bending moment, for this we need to find the first step. So step 1, we need to find the load intensity. Okay, W or Q, anything you can take, load intensity. So it's given by P by A, and A is the area of footing because it is applying in the whole area. Okay, not in the column, just it is applying in the whole area. So P will be 1500 is given, but we have to multiply it by 1.5 factor of safety. Okay, because it's not given that is the factored load. If it is given in the question that it is factored load, so only axial load is given, so we have to take the factor of safety. So 1.5 into 500 divided by area is 2.75 into 2.75. So if you do this, you will get around 297.52 kilonewton per meter square. Okay, please be very careful with the unit whatever you are doing. Okay, so it's given as 297.52 kilonewton per meter square. This is the load intensity. Okay, that means if this is the footing, so its whole area, the Q is given as 297.52 kilonewton per meter square. Okay, Now for the, what we need to find out, we need to find out the factored bending moment. Okay, so for this, what we will know, that this factored bending moment, if we cut a section XX, it will only, so let us, okay, so it will only act in this area. Okay, means if this is our footing, okay, this is 2.75 and this length is 500 mm, okay, and this is meter. So it will act in this area. Okay, so it will act like a cantilever, means if this is the length, this is the unit, so this is the, it will act like in this area. So for this, what is the factored moment? We know for a cantilever it is WL square by 2. So W is the load intensity, okay, it's given as 297.52. okay, now we have to find the L. So this length we have to find out, this one. Okay, so how can you find out? Total is 2.75. okay, if we deduct 500 from it, we will get this length and this length. Okay, so divided by 2, we will get this one. So L will be 2750 or 2.75 meter minus 500 mm, that means 0.5 meter. Whatever we will get divided by 2, we will get 1/2. Okay, so you will get around 1.125 whole square by 2. So the answer will be around 188.274 kilonewton meter per meter. So please mention this, look at this, it's per meter because kilonewton meter is the bending moment, per meter because we are finding out on this area, we are not finding out the whole area. Okay, so we are finding out for 1 meter of length. Okay, so per meter the bending moment is 188.274. okay, but our footing is how many, what is the length of the footing? It's given as 2.75 meter. Okay, because we are finding out only for 1 meter, 188.274. so if we find out the 274, so mu will be okay, so mu will be 188.274 into 2.75. so if you calculate, you will get around 517.76 kilonewton meter. So this is your answer. Okay, so don't get confused. So if you see, so our answer will be A, 517.76 kilonewton meter. This is our factored bending moment. Okay, so simple, if you know the formulas and all, just you have to put it and you will get the values. Okay, okay, so next let us go to the next question. So it's given as the post tension beam 400 mm into 500 mm in 10 meters long is provided with straight tendons which are tension to 1050 Newton per mm square at the jacking end. The loss of pre-stress at the end of the beam remote from the jack is, so to find out the loss of pre-stress. So it's a pre-stress numerical, so it's only for B.Tech. Okay, I think diploma holders will not get this question. Okay, so we have to find out the loss in pre-stress. Okay, so loss in pre-stress, in which there are several loss, there are anchorage slip, there are friction, elastic shortening. So we have to find out, since wobbling correction factor is given, you know we have to find out the friction loss. Okay, and also you can see the question, so at the end of the beam remote from the jack. Okay, so why friction loss? So when we pull the tendons, okay, the high profile tendons, so the force gets slipped due to some friction, okay. So for this we have to calculate the loss. So the formula for loss in friction is given as F into e to the power minus mu alpha plus kx. So since this value is very small, finally we will get almost same value. So for ignoring the complication, we can use this formula F into minus mu alpha plus kx. Now mu is the coefficient of friction, okay. Alpha is the angle at which these tendons are jacked, okay. So K is the, it's given wobbling correction factor. Wobbling correction factor is used for, when the tendons are jacked, okay. So if it is curved, okay, so there is not much K, but if it is straight, due to the straightening or stretching, okay, there are some losses. So this is the correction factor for this loss, and x is the position in which we have to find out the friction, okay. So in the question, angle is nothing is given, so let us consider it's a straight one, so angle is 0. So if it becomes 0, ultimately this whole term become 0. So finally we will get the formula as F into K into x is the position, so it's given the end of the beam. So if you see the question, it's given at the end of the beam, means you have to calculate the whole length. So whole length will come, okay. So F, it's given in the question directly, it's given that tension at 1050 Newton per mm square. So we don't have to find, it's given in the question. So 1050, K is given is 0.30 per 100 meter, okay, 0.30 per 100 meter. So that means 0.3 per 100 meter, okay. And L is given the total length of the beam, which is 10. So if you calculate, you will get all in Newton per mm square, 31.50 Newton per mm square. So this is the answer. So your answer is 31.5 Newton per mm square. So this is very easy, because only you have to know what are the terms that's given, otherwise the calculation is very easy, okay. So let us move on to the next question. It's given as, which of the following types of riveted joint is free from bending stress, okay. So if you have seen my previous lecture on the steel structure, it's given there are two types of joint mainly. One is lap joint, okay, another is, this is lap, another is butt joint, okay. So this is butt joint, but you cannot just join a butt joint like this, you have to give cover plate. So this is a single cover and this is a double cover, okay. So what is the question? It's given that riveted joint free from bending stress. In riveted joint, these are rivets, okay, which is given, you can here also, this is rivets, okay. So it's given as the riveted joints free from bending stress, means no bending stress is developed. Now bending stress is developed due to bending moment, okay. So if in a connection there is no bending moment, that means no bending stress. So if you see in a lap joint, okay, this is one force and there is another force. These two forces are never in the same plane, ठीक है sir? This is not in the same plane, because there is one distance is generated between the two forces. So obviously a couple will come into act, and that's why in lap joint a bending moment is generated, so it is not free from bending stress. Now butt joint, it is single cover, okay, though the two forces are in the same plane, but due to these two forces, some force may generated in this cover plate also. Okay, now if this force is generated in the cover plate, there is no extra cover plate at the bottom to counter this force. Okay, so that's why a couple may generate in the single cover, but in the double cover there is no couple between the two main forces, and if some force is generated in this one, so it will counter by the bottom plate. Okay, so this Bird unit double cover plate is the best one because it's free from all the bending moment and bending stresses. Okay. Okay. Now the next one is given as the modular ratio. Okay, in terms of the permissible stress due to bending in concrete. So M is given, actually it's by ES by EC, it means modulus of elasticity in steel by modulus of elasticity in concrete. It happens when you give a composite member, for example a RCC. We just make some two structure, means one structure with two material, one is from concrete and it's from steel. Okay, so for this type of composite structure a modular ratio term comes into act. Okay, so for this M, it is given in the code directly that it directly depend on the sigma CPC, that means compressive stress due to bending in concrete, and okay, and it's given as 280 by 3 sigma CPC. This is a very common and easy question and I think everyone should know it. 280 by 3 sigma CPC. Okay, this is only for working stress method. Okay, it is used in the working stress method, it is not used in the limit state method. Okay, only working stress method, so it's very easy. Okay, now it's given the zone factor. Okay, it's IS 1890 2002 for B.Tech if you have completed your earthquake engineering. Okay, so you will get this IS code. So for severe and very severe seismic intensity is, okay, so there is one table in this IS code, it's given for all the zone. So zone 2, starting with zone 2 because there is no zone 1. Okay, zone 1 and zone 2 have merged, it's for low. Zone 3, it's for moderate. 4, it's for severe, and 5, it's for very severe. So the Gauhati, the Assam comes in the very severe zone of earthquake. Okay, so the formula, the value for the seismic intensity Z is given as 0.1 for low, 0.16 for moderate, 0.24 for severe, and 0.36 for very severe. Okay, so in the question it's directly given, it's 0.24, 0.36. Okay, so it's easy if you just have to know all these values. Okay, now another easy question came, it's that the flexural strength of concrete as per IS 456 2000. Okay, now there is one is given as the compressive one, it's EC. Okay, it's given as the 5000 root FCK for the compressive, and for the, you can say in the compression, and for tension it's given as 0.7 root FCK because concrete is very weak in tension, so value will be very minimum. Okay, so it's directly given 0.7 root FCK, nothing to be understand about it. Okay, okay, the last question it came that the effective throat dimension of a 10 mm fillet weld made by shielded material. The thread dimension is the thread thickness. Okay, if you have seen my previous steel lecture, I've mentioned it that if it's two fillet joining to mate, okay, this is the welding part. Okay, this is the size of weld, and this dimension is the effective throat thickness. Okay, and effective throat thickness is given as 0.7 into size of weld. So in the question it's given a 10 mm fillet weld, so it's very simple, 0.7 into 10 will get 7 mm. So it's a simple question. Okay, so these are all the question from the RCC part. So I've completed this structure 20 question. I think 20 question I have covered. Okay, so we'll do some more question papers on different examination in the upcoming videos. Thank you. Thank you everyone for watching the video. Please follow our page for more civil engineering videos. Please follow us on Facebook. Do not forget to hit the like, share and subscribe button and press the bell icon to never miss an update from CSL. Thank you.